Okay, I have the cholesterol dataset open again. Apparently the old video got really badly out of sync. I didn't know that at the time. I tend not to watch myself back. It's a little bit painful. So we'll have another look again because that video is a couple of years old now. I honestly can't remember what I did, so I may do it slightly differently. So what we've got here is cholesterol, which is our outcome variable or our dependent variable. There's another word I'm forgetting, which we're trying to predict, a response variable. That's an outcome, response, or dependent. We've got a couple of predictor variables or independent variables, and they would be weight and age. Now, if you look at weight or age separately with cholesterol, so you could do this with a simple linear regression, you will find that both of them are significant. But the question that we might want to ask is, if we have already adjusted for weight, does age still matter? So are they both important at the same time, or is only one of them really important? So to have a look at this with a model, we're not going to use the regression dialog. You actually can do this. There's usually lots of ways you can do the same thing, but just for consistency and to make something which works for a lot of different cases, we're just going to use the general linear model. So I'm going to take these variables out. Let's start off with a simple model with just cholesterol and weight and age as our covariates. So any variable which is continuous is called a covariate. Our model in this case can probably just stay as is because it won't fit an interaction term if we don't have any factors. In terms of saving, depending on which class I'm teaching, sometimes I look at the unstandardized residuals and sometimes the standardized. In practice, I tend to use the standardized, but the unstandardized can be a little bit more intuitive to understand. So we'll have a look at both of those and look at the difference. So we want our predicted values and our residuals, one or the other, or both if you want, I don't mind. Options. Now you may want the parameter estimates out. So this is if you wanted to write the equation. Oh, I probably can't continue. So if you actually want to get the numbers out so you could write your own equation, that's the parameter estimates. And there's a whole lot of other things you can look through here. I'm going to tick residual plot and see what it does, but often with SPSS you want to do your own plots separately. So let's go OK. Yeah, that's not good. Okay, so we've got the null hypothesis in each case is that there is no relationship. So there is no relationship between weight and cholesterol once age has been adjusted for. And we're looking just for a simple linear relationship, just a straight line, because that's all we've added in. And then we've got a null hypothesis for age, is that in that there is no relationship between age and cholesterol once weight has been adjusted for. Weight is significant and the age is not. So it's saying that once we've adjusted for weight, the age is actually no longer important. If you just looked at age by itself, it probably would be significant. So this is where you get the difference between looking at things separately and looking at them all together. And usually the preferred practice would be to look at things all together. So, and down here we've got our parameter estimates. So if you wanted to write out the equation, these betas are what you would use. So it's saying that cholesterol is equal to, on average, 4.4, or 4.5 if you're rounding, plus 0.044 times your weight. So for every extra kilo you have on you, your cholesterol is going up by about 0.044. Now we've also got an adjustment here for age, but as that was not significant, I probably wouldn't keep it in the model. I'd probably just take it out and run the model again. I'm not going to do that now because we've still got a couple of variables, gender and abdominal fat, which we haven't looked at yet. And I'll do that in the next video, and then we might take age out and see what happens. So that's our model. What we want to do now is just check our residuals and check that the model is really a good fit in the first place. Is it a good idea to do this model? Is it the right choice? So what we have here are the three columns for what I ticked. We've got our predicted values. So for this first person, based on their weight of 90 kilos and their age of 83, they had a predicted cholesterol of 6.26. Their actual cholesterol was 5.83. The difference between their actual cholesterol and their predicted value is the error or the residual. So we were out by negative 0.42. That doesn't sound quite right. Oh no, that's okay. So that's the raw error. The standardized version takes all these raw errors and it fits them onto a normal 0-1 distribution. So if we have a look at that, we can do a graph just to show you what I mean. So I'll look at a histogram, reset that. If I look at the raw residuals, these are the actual amounts that I was out, well not me, the model was out. So anyone here was spot on at the 0. These people, their cholesterol predicted was out by about 0.5, and these ones were out by about up to 0.75. If we have a look at the standardized residuals, that's actually the same pattern. It's funny, it looks different. I think it's been broken up into different bins. You should see the same pattern with the raw and the standardized residuals, but it's been fit onto a normal 0-1 distribution. So instead of the actual amount that they were out for the cholesterol, we've got the standardized value, which would go from -3 to +3. Here we are only going from -2 to +2, so there were no predictions which were very wrong. We don't have any extreme values. Now the things that we want to check with the residuals are that they are approximately normal, that they are randomly scattered, and that there's no increase or decrease in the variance. So to check the normality, you can do some normal, you can do a test for that. You can do a PP plot or a QQ plot. I'm not going to do that here. I think it's easier in this case just to look at the histogram, but you can fit the normal curve on it if you like to help you interpret it. So in this case, they're not quite normal. We don't have any extreme values, and there's nothing particularly wrong with it. It doesn't actually look skewed, or there's no outliers. It actually doesn't even look overly peaked, only pulled up. So I'm not even sure there's any kurtosis really in this. It just doesn't look quite normal, and this might be because our model is not fully formed. It might be because we've got a small data set. There might be something else going on. We might have really consistent results, so there's just not a lot of error in there, and we can see that we don't have any residuals closer to the -3 and 3 mark. So they're not quite right, but there's nothing terribly wrong with them. There's no severe violations is what you might write down. Now the other thing that we want to look at is what are the errors over all of the predicted values? Are there any patterns there? So to look at that, we would do a scatter plot. I'll just reset that. So we're looking at, for every predicted cholesterol level, so I'm going to take the predicted values and put them in the x-axis, what kind of errors are we seeing? So we put our predicted values on the x-axis and our standardized residuals. You can use your raw residuals as well. It doesn't matter, you'll see the same patterns. The reason I like the standardized ones is because I know that they should be going from -3 to 3. So then it's really easy to look at it and go, oh, that's a bit extreme. That's at -4 or -5. So I prefer that, but you could use the raw ones if you find that more intuitive. Now what we're interested in is, are the errors either side of 0? So sometimes you'll find it helpful to actually put a line on at the 0 mark. So let's add a reference line at 0. So what have we got here? They do appear to be randomly scattered about. There's no evidence of a curve, and that would come out really strongly in the residuals if there was one. There's no increase or decrease in variance. We've got sort of the same amount of error for these low cholesterol values as we have for the high cholesterol values. We do have these two very low ones, but they're not that far away from the data. So there's nothing very wrong with the residuals here. So I think our model is probably looking okay. So that's our basic model with just weight and age, and in the next video I'll have a look at adding in our factors, gender and abdominal fat.